Okay. Hi, everybody. Thanks all for listening in. So, in this presentation, what I want to do is continue to talk about how things move in space. Um, in the last video, I talked about how the motion of astronomical objects can be understood using a few different sets of rules: Newton's laws of motion and the universal law of gravitation. The Newton's laws, which we talked about last time, are universal tendencies of motion. Basically, the idea that objects tend to move in straight lines unless they interact with other objects, which creates forces that cause objects to accelerate or deviate from straight line paths. Now, that's a general framework and applies to the motion of basically any object. The one thing we didn't really specify there was what are the strengths and nature of those interactions or those forces. That is not encapsulated in Newton's laws. What the forces are comes from other physics. And on Earth, there's a number of different forces that can exist. A lot of them involve the interactions between atoms and electrons within our bodies. However, in space, most of the interactions, most of the forces are due to one particular physical process: gravity. And the universal law of gravitation is basically the prescription for how to calculate a interaction force due to gravity. Now, this gravitational interaction has just a few key properties. It's often expressed using a diagram like this with a couple of objects or a formula like this. Now, formulas, I know, can sometimes be a little intimidating, but basically this formula sums up a few key properties of this interaction. And whether you want to understand this in terms of words, pictures, or equations is up to you. The first aspect of this force that is important is that it occurs between any pair of objects. Here we just have two balls, one marked with M1 that indicates mass 1, one marked with M2 that indicates mass 2. The first characteristic of the gravitational interaction between these objects is that the interaction always causes an attraction. That is, the force on object 1 created by mass 2 points towards mass 2. So mass 1 is attracted to mass 2. It feels a force in this direction. Mass 2 feels a force due to mass 1. It's this force 2. So this mass 2 is also attracted towards mass 1. Now, notice already that this prescription basically already makes sure that we satisfy Newton's third law. It means the two forces are in opposite directions, and furthermore, we specify that this force is equal for the two. The strength of the pull is the same, but the directions are opposite. Every force has to do that, so it's doing that by design. But then there's the question of what the strength of these forces are. And the strength of the force depends on two parameters: the masses of the two objects and their separation. The force gets stronger if you increase the mass of either object. In the formula down here, the force is equal to a factor g, which is just a number, times the product of the two masses. So if I make mass 2 bigger, the force gets stronger. If I make the mass 1 bigger, the force gets stronger. So more massive objects have stronger gravitational forces associated with them. The other thing, though, it depends on is the separation between these two objects, which is indicated here by the letter D. And it turns out as you pull the objects apart, the force gets weaker, but it does so in a very specific way. If you take two objects that are originally separated by, say, a meter and pull them apart so they're now 2 meters apart, the force doesn't go down by a factor of 2, it goes down by a factor of 4, or 2 times 2. This is indicated in the formula by the saying that the force goes like 1 over d squared. So as d gets bigger, the force gets weaker because you have a bigger number in the denominator, and it drops off by a factor of d times d. So if you pull them 3 times as far apart, the force goes down by a factor of 9, and so forth. Now, the reasons that this force has these properties is something we can get into later. It actually allows for a different sort of understanding of this tied to geometry, which we'll get into when we talk about black holes. But for now, you can just understand this as the observed property of this force. It has been measured in the lab. It is consistent with how all sorts of objects in space move, both natural and artificial. Now, an aspect of this force that is problematic, or at least starts to sound like it's really complicated, is that this applies to every pair of objects. Every pair of objects has this attractive quality. And that sounds like any evaluation of forces is going to be very complicated, because it means that there's a force on the Earth from the moon, a force on the Earth from Jupiter. There's a whole infinite number of objects in our universe. Do we have to calculate the force from all of them? And in practice, the answer is no, because the interactions, the force from different objects, depends both on how massive that object is and how far away it is. And those two factors together mean that these forces can have extremely different strengths. And in a lot of cases, we can basically pretend that only one object is relevant to calculating the gravitational acceleration of a body. This is an approximation because, of course, there are forces from other bodies, but it's often a pretty good one. And let's just look at a specific example to kind of show that. The force of gravity we're all most familiar with here on Earth is from the Earth itself. Things fall down. The Earth is below us. That is due to the Earth's gravity. But you might go, wait a minute, the sun is really big. The sun is really massive. Shouldn't we feel the sun's gravity to some extent? Like, if the sun's directly overhead, isn't that pulling us up? And if it's down below our feet, isn't it pulling us down? Isn't that relevant? Well, that's a reasonable question. And we can actually look at that quantitatively. We can evaluate the relative strengths of the forces from these two objects. So we have to then consider the two parameters in this formula, the mass of the object and how far away it is from us. Note, we can particularly consider the force on one of us, just a person. So for that, it's going to be the mass of the planet or the star times the mass of the person, which is the same, divided by the distance to the big object squared. So these are the two things that differ for these two forces. So we have to consider that. We do know the mass of Earth and the mass of the sun. The mass of the Earth is big. It's 6 times 10 to the 24 kilograms, so 6 followed by 24 zeros. But the mass of the sun is much bigger. It's 2 times 10 to the 30 kilograms, so 2 followed by 30 zeros. So it works out that the sun is about 300,000 times more massive than the Earth. Now, this is one of the reasons I try to be specific when I'm comparing sizes. In terms of diameters, distances across the body, the sun is only about 100 times bigger than the Earth. But in terms of mass, which is relevant for motions, the difference is about a factor of 300,000. Okay, so the sun is more massive, should have more gravity. That's fair, but we also have to consider the distances involved. Now, the distance to the Earth is actually a little non-trivial because there's bits of the Earth that are right under our feet, but there are also bits of the Earth that are all the way in Australia, which is quite far away. So when we're considering gravity, we have to consider the distance to the average bit of Earth. And it turns out the distance to the average bit of Earth is basically at the center of the Earth. So our average distance to the Earth is equivalent to the Earth's radius, which is about 6,400 kilometers. The distance to the sun is more straightforward because it's basically the distance from the Earth to the sun, which is an astronomical unit, which is 150 million kilometers. So the sun works out to be about 25,000 times further away than the Earth is, basically. Now, you might go, oh, the distance is only a factor of 25,000, whereas the mass is different by a factor of 300,000. That still sounds like the sun wins. But remember, the gravitational force doesn't go like distance itself, it goes like distance times distance. So we have to take these numbers and multiply them by themselves. 6,400 times 6,400 gives you 3.6 times 10 to the 7 kilometers squared. 150 million times 150 million gives you 2.3 times 10 to the 16 kilometers squared. This number is 600 million times bigger than this number. So the distance factor for the sun is 600 million times bigger than the one for the Earth. And that's important because it's the ratio of these two numbers that determines the force. And if you evaluate those two, that ratio, what you find is that that ratio, mass over distance squared, just shown as m over d squared for sake of fitting it on the page, the number you get here for the Earth is about 2,000 times bigger than the number you get here for the sun. So that means the Earth's pull on us is about 2,000 times stronger than the sun's pull on us. So when we're considering the motion of individual objects, like the falling of something off a table, the Earth's gravity is really, really important. The sun's gravity is a pretty small correction to that. You only need to start worrying about it if you want to measure it to better than, 1/10 of 1%. So this shows that often we can ignore some other objects. But at the same time, I want to make it clear the reason this happened was because the masses and the distances were at the right because the mass ratio and the distance ratio had certain properties. It is not true that just because an object is further away from us, it's less important. The way to demonstrate that is to consider the motion of the Earth. The Earth is a pretty big thing, and it's got two really obvious sources of gravity. We have the moon and we have the sun. The moon is closer to us than the sun, so you might think it's more relevant for how the Earth moves. But because of the mass of the moon and the mass of the sun and the explicit distances, that turns out not to be the case. And again, we can go through the same sort of comparisons. We know the mass of the moon. We put people on it and measure the gravity. It turns out that the moon is less massive than the Earth, not too surprising. And the sun is actually 30 million times more massive than the moon is. The moon is closer than the sun, but only by a factor of 400. We talked about this before. The sun is about 400 times further away than the moon. That's not as much as that is a smaller factor than what we were considering when we were considering our motion on the surface of the Earth. And so if we take the square, this number for the sun is only 160,000 times larger than this number for the moon. That is smaller than the 30 million in the mass ratio. So if we consider mass over distance squared, we find that the gravitational pull of the sun is 200 times bigger than the gravitational pull of the moon. That means that our motion, to a fair degree of accuracy, is determined by the gravitational pull of the sun. And the moon is there. It does affect our motion, but it's a small correction to it. So to first order what's called an approximation. So at an approximate level, and a pretty good approximation, the motion of the Earth is driven by a force coming from the sun. Now, that is actually important because it means that the force experienced by the Earth almost always points directly towards the sun, and that means the acceleration always points directly towards the sun. The change in motion, the change in the velocity direction, always points towards the sun. And that force gets stronger if the object gets closer to the sun. Now, this is true for basically most objects in the solar system, be they planets, be they asteroids, or be they comets. The thing is, if you have this property where the sun is basically the dominant force acting on you, that actually puts pretty strong constraints on how you can move. There are only certain allowed paths, certain allowed trajectories that are consistent with that basic force. And what that results in is objects where the sun is the dominant source of gravity following particular trajectories. These are called orbits because they go round and round. And it means that all of the planets and even asteroids follow paths that go round and round the sun. And the thing is, the shapes of all of these paths have certain things in common. They clearly differ in size and to a certain extent in shape. But it turns out that all of these orbits have certain things in common, which is just due to the fact that the sun is the primary thing pulling on. Those things they have in common about their trajectories, about their orbits, are what are called Kepler's laws. These are a set of rules that objects follow based on how they move around a particular strong mass. That is the dominant source of gravity. It was originally developed to explain the motion of planets in our solar system by Kepler. And it's basically they're all consequences of the universal law of gravitation. And turns out that versions of these three laws do apply to any other system where there's a single big central mass. Although you have to adjust things a bit. And so I want to go over these three rules. The first of the rules describes the shapes of these orbits. It says that all orbits around the sun are shaped like ellipses with the focus with the sun located at one of the foci of the ellipse. What's a foci? We'll get to that. The second and third rule describes the motions around these tracks. The second rule says that as the planet goes around the sun, it sweeps out equal angles and equal times. And the third rule says that the total time it takes the planet to go around the sun is set by basically the size of the orbit in a particular way. Now, there's a lot of jargon here. We'll try to demystify each of it. So let's first consider the first rule, what's called Kepler's first law. It says that orbits are shaped like ellipses. What's an ellipse? An ellipse is a curve that is kind of like a generalization of a circle. The classic way it's laid out is that you imagine putting two pegs in a surface. It could be a whiteboard, it could be a sheet of paper or whatever. You run a string around those two things and stick a pencil in, pull it taut, and pull it all the way around. And if you do that correctly, it's often easy to not do it correctly, you will create a closed figure, which is known as an ellipse. And these 2 points are what are called the foci, plural of focus, of the ellipse. Now, to say this is a generalization of a circle. If you take these two pins and put them on and move them really close together, what you're doing is basically drawing a circle, because basically you're drawing a line at a constant distance from those two pins. But as you pull them apart, the fact that you have to run string between the two of them causes the curve to be a little sharper or a little smoother. Now, if we were talking about just a circle, the only way you could change the shape of the circle is by making the string longer. So the only way to change the properties of a circle is to change its size. In this case, we can both do that, make the string longer or shorter, but we can also change the distance between the two foci. So there's actually two different ways the shape can change. On the one hand, and so this is the two different properties of an ellipse. The first property of an ellipse is what's called its semi-major axis. It's basically half the distance, across the longest axis of the ellipse. This is basically a measure of how big your ellipse is. If you have a small semi-major axis, the ellipse is small. If you have a big semi-major axis, the ellipse is big. This describes size. The other parameter is what's called the eccentricity, which describes basically how elongated the ellipse is. If the eccentricity is 0, then that corresponds to the case where the two foci are right on top of each other, and you have a circle. If you start pulling them apart, you get increasingly large values of eccentricity, and that creates an increasingly elongated structure. So eccentricity is basically how circular to elongated the orbit is. And all orbits in our solar system can be described that way. If you look at the orbits of the planets in our solar system, they look mostly like kind of sort of circles. But if you look at things like, say, Mars, you might be able to notice it's a little bit more elongated this way than this way. So it actually has a bit of an eccentricity. The other thing you will notice about Mars and also Ceres to an extent is that Mars doesn't stay, that the sun is not located at the center of that ellipse. Notice it's getting further from the sun here than it is here. So the sun is not located at the center of the ellipse. It's actually located at one of these two focus positions. So as you make the eccentricity big, the orbit actually gets very close to the sun and very far away. This is particularly important for, say, comets, which have large eccentricity orbits. They tend to come racing in from the outer solar system, swing by the sun, and then go back out. Okay? So, and the thing is, all these shapes can be well approximated by ellipses. They're slightly off due to the interactions with the other planets, but it's a pretty good approximation. Great. And just to say, this is more universal than just our solar system. Anytime you have small objects orbiting a big object, you see the same thing. This is a fairly dramatic example. This is again a picture or illustration of the stars near the center of our galaxy. And the lines indicate how far, basically indicate their motions over the course of a couple of decades measured by various instruments. And what I'll draw your attention to is this little yellow ellipse. This is the path of this particular star, which is an elliptical path that is centered, that has at one of its foci an extremely massive object. There is a supermassive black hole in there. And that location is not just the focus of this ellipse, it's also the focus of the partial ellipses that all of the other orbits are following. So this basic elliptical motion is seen well outside our solar system as well. Okay. Okay. The second rule, or Kepler's second law, says that planets move faster when they're closer to the sun, especially if they're on elliptical orbits. The way it's often phrased is they sweep out equal angles in equal amounts of time, which is just a nice quantitative way to describe it. So if you have an object orbiting the sun on an eccentric orbit, when it's far from the sun, over a period of 2 months, it might move this much. So it sweeps out a fairly small angle. So this triangle is fairly tall, but fairly skinny. As it gets closer to the sun, like over here, in 2 months, it sweeps through a bigger angle. So its triangle is shorter, but wider. Now, this is again observable property. It's a little hard to see in planets because even Mars isn't that eccentric, but we can see it really clearly in comets. This is the track of the comet 2P Encke, which basically moves between the asteroid belt and the orbit of Mercury. And as you track this, you find it moves very slowly out here when it's in the asteroid belt, then comes diving through the inner solar system very quickly. This is also seen outside our solar system. Again, going back to that star in orbit around the very massive thing in the center of our galaxy. This shows the observations. It's showing the elliptical trajectory of the star, and the different things give you the dates when the observations were made. So it was first seen here in 1992, got to here in 1994, went down, down, down to here in 1999. So you can notice it took about 5 years for the star to go through this much of an angle. Then it was here in 2000, here in 2001, here in 2002.2, and here in 2002.6. So it swept from here all the way over to here in a single year. It's clearly moving faster here when it's close to the big supermassive black hole, which is thought to be here, than it was moving over here, where it took 5 years. So we see this, and it's actually fairly sensible. The reason this happens is because if you imagine a comet or a star, as it's coming in, the sun is pulling on it in its direction of motion. So it's actually falling towards the sun. It's speeding up as it gets closer and closer in. Then it whips by the sun. As it whips by the sun, it's now moving away from the sun. So the sun is trying to pull it back, which is slowing it down. It eventually basically stops in terms of its radial motion, then starts falling back in, speeding up. So this is actually kind of sensible. Now, the final law, Kepler's third law, is more about the average motion of these things. It relates the total time that it takes for the planet to complete an orbit to the size of the orbit. Notice this doesn't involve eccentricity at all. Doesn't matter what the eccentricity is. Just matters what the semi-major axis is, which is, again, just half the length across the longest direction of this orbit. Turns out that bigger orbits take longer to complete. But more specifically, for planets in orbit around the sun, or objects in orbit around the sun, the period squared, so the period times the period, equals the semi-major axis cubed. So the semi-major axis times the semi-major axis times the semi-major axis. This is the general rule. And it means that if the semi-major axis is say twice as big, the period doesn't just go up by a factor of 2, it goes up by more. Now, again, this is something you can check yourself. You can go on to places like Wikipedia, find the semi-major axes of the planets in AU, here they all are, and find their orbit periods, how long they take to go around. And they range from a quarter of a year for Mercury to over 100 years for Neptune. And you can just calculate the cube of the semi-major axis and the square of the period, and what you will find is the same number in all these different cases. The value of this number is different for each object or each planet, but it's the same. A cubed and period squared are the same. This also works for any asteroids or comets, and I encourage you to try them out and just see what you get. Now, a thing about this rule is that it means it takes longer for planets to go around if they're further from the sun, which probably should make some sense. However, this also has implications for how fast these objects are traveling. The thing is, the semi-major axis tells us the length of the path it's taking. The period says how long it takes to travel around that path. Taking those two pieces of information, you can calculate the average speed of the object around its path. Now, that can vary a little bit if the orbit's eccentric, but it's still a good measure of the average orbit speed. And when you do that calculation, you actually find something interesting. Objects close to the sun, like Mercury, are traveling very fast, 47 kilometers per second. Earth is traveling at 30 kilometers per second, which is still pretty fast. Neptune is going at 5 kilometers a second. The further you are from the sun, the slower you move. This is because the force of gravity drops with distance. So in addition to being further away and thus having a longer path to travel, the more distant planets are actually moving slower along those paths, which is an important thing to keep in mind. Now, this rule, as I just stated it, was only for objects in orbit around the sun. But a similar rule applies for other objects. It is still true that the period in years squared is proportional to the semi-major axis in AU cubed, but there's a constant out in front of it. So it's still true that the period and the semi-major axis are related, but now it's not just going to be 1-to-1. There's going to be a number involved. Quick way to demonstrate this. Let's look at Jupiter. Jupiter has a collection of moons in orbit around it. The 4 biggest ones are Io, Europa, Ganymede, Callisto. We know the sizes of their orbits. They're small by comparison to the orbits of planets, but that's fine. And their periods are fairly short. They're a fraction of a year. They're like mostly a week or two. But I can still calculate A cubed, and I can still calculate period squared. Now, what you will notice here is I have 2 times 10 to the minus 8 for A cubed, but I have 2 times 10 to the minus 5 years squared. Okay, so this is about 1,000 times smaller than this. If I look at the next moon out, I get 9 times 10 to the minus 8 and 9 times 10 to the minus 5. Oh, the ratio is again 10 to the minus 3, 1 in 1,000. And that works for all of them. So in this case, one doesn't equal the other, but the ratio of one of these to the other is a constant of 0.001 AU cubed per year squared. What that number tells us is the mass of Jupiter. And that should make some amount of sense. The way to think about it is, let's just consider one moon. Callisto is at 0.0127 AU, and it has a period of 0.05 years. You can do the calculation here and again get a cubed and period squared. The thing is, this period, even though it's short, it's much longer than what the period would be if period squared equaled a cubed. If you had something with this semi-major axis orbiting the sun, the period would have been 0.0014 years. It would be much shorter. It therefore takes Callisto much longer to go around Jupiter than it would take to go around the sun, given just where it is. That is because Jupiter is much less massive than the sun, so its gravitational pull is weaker. Turns out this constant that relates these two numbers is essentially the mass of Jupiter relative to the sun. The mass of Jupiter is 0.001 the mass of the sun. Now, if you are a formula-loving person, this slide just gives you a quick sense of how you actually do that. I am not expecting you to memorize this formula, to be clear. The mass of the central body is basically set by the semi-major axis of an orbiting object cubed divided by its period squared times a numerical factor that depends on this universal gravitational constant. Basically, it means, though, that since the constant was 0.001 for Jupiter, the mass of Jupiter is 1/1000th the mass of the sun. So Jupiter is much less massive than the sun, which makes sense. It's way smaller. This is extremely valuable because it allows us to figure out the masses of objects far away. Let's go back to this thing in the center of our galaxy. This orbit for this star has a semi-major axis of 1000 AU. If we use the rule for our own solar system, we can stick in this number. We can basically cube this. We get a very big number, AU cubed. We then say, the period squared is that number. Take the square root. We would get a period of about 30,000 years. The actual period is 15. This thing is whipping around whatever the central mass is extremely quickly. That means the gravitational force on it is much larger. And so the mass of the object at the middle is much larger. You go through the math, it turns out that the mass of the object in the middle has to be about 4 million times the mass of the sun. That's how we know its mass. Turns out that also explains the motions of most of the other stars in this region. So it's a consistent story. So I hope I've given you a sense of why these rules are important. They allow us to figure out certain things about distant stars, distant planets, etc. I do want to make the, again, point that this only works if there's a single dominant source of gravity. And that's not always true. Sometimes when objects fly close to other bodies, you actually do have to consider the gravitational interactions not only with the sun, but also with, say, Jupiter. And this can produce more complex trajectories. So these rules are useful, but they should not be overextended. Anyway, thanks all for your attention, and I'll see you all next time.